Hi math students, we're back to finish up our video or our second video in the series of deriving the formula for derivative. So in the first video, we made it up to example 1, part A, and I'm just recapping the final answer that we got here. We realized that if we graph the function f of x equals x squared minus x, which we did, and I just graphed it again down here, that the slope of the tangent line at any point xf of x on that curve, on that parabola, is given by this function 2x minus 1. So 2x minus 1 is the derivative of the function. This is going to give us the slope of the tangent line anywhere on this graph, anywhere on this parabola. This function will give the slope. We just have to plug the value of x where we want to find the slope around the curve, and we will get it by using this. So this is what we're going to do in part B. It says, find the slope of the tangent line. So let me highlight that. Find the slope of the tangent line to the graph from above, the parabola f of x equals x squared minus x, and then they actually give us a specific point at the point negative 1, 2. Now we can verify that the point negative 1, 2 indeed is on this graph. If you just look, so if f of x is equal to x squared minus x, and you wanted to find the y value when x was negative 1, then we would just plug that in. Negative 1 squared minus negative 1 indeed is 1 plus 1, which is 2. So this is just verifying that indeed this point is on this parabola. So if I highlight that point, say here's negative 1, 2, like right here. So when we find the slope here of the tangent line there, it should be negative. If it's not negative, because you can see that tangent line is going to have a negative slope at this point. If we don't get a negative, then that's a signal that we probably did something wrong up here. So let's take a look at this. So this is our notation. What we're going to do is we're going to use the notation from up here, but instead of having this generic point x f of x, we're going to plug this point in negative 1, 2. So the notation will look like this. Slope of the tangent at the point, here we go, negative 1, 2 is equal to, now I'm going to take this is what I'm going to use for slope, and I'm going to plug the x value right here, negative 1, this is my x, I'm going to plug that in right here. So 2 times negative 1 minus 1 equals negative 3. So that's a good sign. We got a negative 3 slope, and this looks like it could be approximately a slope of negative 3. Okay, so again, even though this looks like the equation of a line, it's not. This is not mx plus b. This is just the derivative. I know it has that linear feel to it, but that's got nothing to do with the linear function at this point. It's just the slope. So we just plugged negative 1 into our slope and got negative 3. Now when we get to part C, we actually are going to go to the line y equals mx plus b, because look at what it says. Write the equation of the tangent line. The equation of the tangent line to our parabola at the point negative 1, 2. So now they do want us to write the equation of this line. Okay, so we know that the general equation of a linear function is y equals mx plus b. And we already know that the slope of this line from part B is negative 3. So this is my m. We already know that m is equal to negative 3 here. So I'll plug that in. So y equals negative 3x plus b. And now to solve for b, I'll just stick the point of tangency right here, negative 1, 2. I'll use this point as my x and my y. So the y value is 2, and the x value is negative 1. And when I solve that for b, let's see, this is going to give me a positive 3 plus b. And when I subtract 3 from both sides, I get b equals -1. So my final equation for the tangent line to the curve at this point is going to be y equals -3x minus 1. And again, you can see that that -1 y-intercept seems reasonable. If I extended this line a little further, it would look to be crossing the y-axis at an intercept of approximately -1. Okay, so again, parts A, B, and C, I know we did them on separate videos, but part A was finding the slope of the tangent anywhere along our parabola. Part B was finding the slope of the tangent line at a specific point on the parabola. And part C was writing the full equation of that tangent line. Okay, if we flip the page to our final example in this packet, it says, example 2, it says find the slope of the tangent line. Okay, so we're just doing the slope to the graph of f of x equals 2 over x at x equals 1. So they are giving us a specific point. So if I'm comparing this example to the previous example, it's almost as if we're doing parts A and B. They're not asking us to write the full equation like we did in part C, but they are asking us to find the slope of the tangent line and then to do it at a specific point. So again, for my visual learners, the first thing I'd like to do is sketch the graph here of f of x equals 2 over x by using some of our techniques from Unit 1, sketching rational functions using limits. So let's go ahead and take our rational function. Let's set the denominator equal to 0 to see if we have any discontinuities. We do. When you set the denominator equal to 0, you see that x equals 0. If I evaluate f of 0, I get 2 over 0, which shows me a vertical asymptote at x equals 0. So I know that right now I've got, if I'm graphing this, I've got a vertical asymptote at x equals 0. So I'm just going to highlight that. Now let me take a look at my limits left and right of 0. So if I do the limit as x approaches 0 from the left of 2 over x, then I have 2 over maybe -0.1, and that's going to be -20. And if I let it be -0.01, that's going to be -200. And the closer and closer I get to 0 from the left, these values are going to be getting very large in the negative direction. So we'll go ahead and say -infinity for that. So 0 from the left, we're going down to -infinity. And then if I do the limit as x approaches 0 from the right of 2 over x, I have 2 over positive 0.1. So I'm going to go ahead and say infinity for that one. So we're coming up here. Okay, what else can I find? Well, I can find horizontal asymptotes by evaluating the limit as x approaches infinity. Well, the limit as x approaches infinity of 2 over x, if I plug it in, is just 2 over infinity, which we know goes to 0. And if I do the limit as x approaches -infinity of 2 over x, I have 2 over -infinity, which also heads towards 0. So I have a horizontal asymptote here at y equals 0. Okay, so basically my graph is going to look like this. Okay, so that gives me a visual idea of what I'm dealing with. Now, they want us to find the slope of the tangent line when x is 1, when x is 1. So if I come over here on the x-axis to x equals 1, well, let's see what my y value is. If I evaluate f of x when x is 1, then f of 1 would be 2 over 1, which is 2. So at the point 1, 2, I am to find the slope of the tangent line. So at the point 1, 2, see, they didn't give me the y value, but it's really easy to find by plugging in. Okay, so you can see the contour of the curve here. If I draw a tangent line there, it looks like it's going to have a negative slope. So in the end result here is that I should have a negative slope of the tangent line. So let's go ahead and start in. I'm going to kind of section this off. Let's start in with our derivative formula. So it starts like this. Slope of the tangent line at any point x f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so now we start in with our limit. So we have the limit as h approaches 0. Okay, we know f of x is 2 over x from up top. F of x plus h would just be 2 over x plus h. So we have 2 over x plus h minus 2 over x all over h. And if I plug 0 in for h, I'm going to get 0 over 0. So I'm going to go ahead and eliminate my complex fraction. I'm going to multiply all 3 parts here, all 3 terms, by these 2 denominators, x and x plus h. So if I multiply this first term by x and x plus h, my second term by x and x plus h, and my third term down here by x and x plus h, then I should be able to reduce my function. So the limit as h approaches 0. Okay, here the x plus h's are going to cross out, and I'm going to be left with 2x minus. Here, the x's are going to drop out, and I'm going to be left with 2 quantity x plus h. And then on the bottom, I just have hx times x plus h. In my next step, I'm going to distribute my -2 through the back quantity. So that's going to give me 2x minus 2x minus 2h all over hx times x plus h. Now my 2x minus 2x will drop out. So that will give me -2h on the top with an hx times x plus h on the bottom. Now the h's will drop out. And when I plug 0 back in here for h one last time, I'm going to get -2 over x times x, or -2 over x squared. And this is the derivative. This is the derivative in terms of x of the function f of x equals 2 over x from above. So this is going, no matter, I could put any value of x in here, and it will give me the slope anywhere I want on this curve. But I want it specifically at this point we've already shown here, 1, 2. So my final step down here to this problem would be slope of the tangent at the specific point, 1, 2, is equal to -2 over, now I'm going to plug in here, my x is 1, so 1 squared, and I'm going to get -2. I'm glad it's negative because visually I knew it was negative. So the slope of this tangent line is -2. Okay, so having seen all of these examples, I know for homework we already did day 1 from the last video, 1 to 6, and now we're going to get days 2 and 3 done. So good luck with that.